The black in my back and my boys do too. And my baby mama trippin' since she need more loot. Every block, every hood, every ghetto got beef. Got a heater on my lap and another.
I am an almighty wizard!
Kinetic energy is the energy of motion.
Kinetic energy is equal to 1/2 mv squared. M is mass, which is measured in kilograms, and V is meters per second, which is speed. Now I'm only going to tell you this one more time, so pay attention. Kinetic energy is equal to 1/2 mv squared. Measurements. M is mass, which is measured in kilograms, or kg. V is velocity, or speed, depending on how you think of it, which is measured in meters per second, or m over s. When you put that together, along with the 1/2 and the square root of v, it makes kinetic energy, which is measured in joules, or J. Now, kinetic energy has to come from somewhere, and that's where my friend potential energy gets involved. Potential energy deals with mass times g times h. G is acceleration due to gravity, and because we're on planet Hallway, we're going to assume that it is 10 meters per second squared. I don't know if I drew that right because I'm upside down, but you get what I'm saying. Meters per second squared. H is the height that you are at. Now, the higher you get, the more potential energy you get, and the highest you can get gives you your maximum potential energy. Let's demonstrate with my friend Philip.
Observe as Philip's thumb is pointed upward when he's at the bottom of the swing. This is because kinetic energy is at a maximum there, because potential energy is at a minimum. Now see how his thumb is pointed downwards at the top of the swing. This is because potential energy is at a maximum here, speed is 0, and kinetic energy is at a minimum.
Now let's show what Philip just did with the help of my art AP credentials. He started at his most highest point, giving him most of his potential energy. When he started coming down, his potential energy transferred into kinetic energy. As Philip kept on coming down, he got to his lowest point, and he had full kinetic energy here, also giving him his total maximum velocity as well. As Philip started coming back up, his kinetic transferred back into potential, and he came up to the exact same height as he did from before because he did not gain any energy. Allow me to demonstrate why people will understand this and not dogs. Tanner, come. Tanner, when does Philip have maximum potential energy? Lie down. You see, he doesn't get it. He doesn't get it.
On a slide, the potential energy is at a maximum at the top, and the kinetic energy is at 0. At the bottom of the slide, the kinetic energy is at a maximum. Observe this example. Notice how Philip's level of fun increases as he goes down the slide. Also, his kinetic energy increases as he goes down the slide as well, reaching a maximum at the bottom.
Now, most slides will have friction in them, which will make you lose your total kinetic energy compared to your potential energy. But because I am a wizard, I made sure that there was no friction on this slide. So it was perfect.
Oh look, it's two young boys playing tennis. Let's go investigate the physics of this phenomenon.
We're not playing tennis.
The kinetic energy of the birdie is at its minimum when it's at its highest point in the flight. This is because the potential energy from MGH is at its maximum here as well. Kinetic energy is at its highest immediately after the birdie is hit. And if the birdie is hit extremely hard, then kinetic energy will be really high, because speed will be really high, and 1/2 mv squared will be much greater. The potential energy here is different from the potential energy on a trampoline, because the potential energy on the trampoline is due to spring potential energy, which has the formula 1/2 kx squared. Now, when Philip is jumping on the trampoline, he has the greatest potential energy when he is at the top or bottom of the system. When he is at the lowest point, potential energy is due to spring potential energy because change in x, the distance from the equilibrium, is at its greatest. Potential energy is also at its highest at the top of the flight because mgh is the greatest there as well. Kinetic energy is at the greatest at the equilibrium point, which can be found using the formula kx equals mg. This is because forces are in equilibrium here, and therefore speed is at its maximum, and 1/2 mv squared is at its maximum.
Jeremy, I believe, missed some of that great trampoline example. So let's explain it to him in further detail. The main thing that is tricky about the string is that the equilibrium is not where the trampoline lies flat, is a little bit below. We find this by finding the equilibrium point, which is when the sum of the forces equals 0. The only forces are mg down from me standing on the trampoline and the spring force from the trampoline back on me. As you can see, this equation simplifies with my mass of 80 and the acceleration due to gravity as 10 to 80 times 10 over k equals x. Now if only we knew the k, we would be able to find out what the displacement is at equilibrium.
K is 4,000.
If k is 4,000, that would mean x would have to equal 0.2 meters. So the equilibrium point in this example is 0.2 meters below where the trampoline lies flat.
Another thing to consider is that change in kinetic energy is also equal to work. The formula for work is Fd cos theta. Since theta is 0, cos theta goes to 1, so we don't need to worry about that. The average force times the distance over which the force is exerted equals to the change in kinetic energy, which is what gives that orange thing the speed to move into the pool. Here's another example.
Kinetic energy! Ah! Ah! It hurts! We hope that you have enjoyed our lesson on kinetic energy. Goodbye for now, and don't forget, do Fd cosine theta, son!
She has souls who cope with all the stress on